Welcome to Physics Dream Team Classroom, College Matrikulasi Pahang Kementerian Pendidikan Malaysia.
Hello everyone! So today we're going to learn the chapter 2, which is kinematics of linear motion. We take an example of a car which is initially at rest, so the velocity is 0. Then the car going for accelerations by 6.5 meter per second square. So in order to calculate the velocity of the car after 8 seconds, so we're going to use some principles contained in this chapter. You might be wonder what's the overview under the chapter 2. So we have two parts. One is the linear motion and the second is the projectile motion. Linear motion is what we call as a one-dimensional, which contains a uniformly accelerated motion. And for the projectile motion, it's a two-dimensional, which contains three parts. One is the projectile launched at an angle theta. The second is angle 0 from the horizontal, and the third is the launch at angle which is vertical, which is 90 degree, which we call as a free falling motion. So what is meaning by kinematics of linear motion? So it is defined as a study of motions of an object without considering any effects that produce the motion. Okay, so this is some of learning outcomes under chapter 2, which contains two definitions. These definitions are the instantaneous velocity, average velocity, and uniform velocities. And for the accelerations, we have three types of accelerations. One is the instantaneous accelerations, second is average accelerations, and the third is uniform accelerations. And then we're going to discuss the physical meaning of three types of graph. One is the displacement time, velocity time, and the acceleration time. So under the first part of the chapter 2.1, we're going to discuss about the instantaneous velocity, the average velocity, and the uniform velocity. So we're going to learn about the terms involving each of the velocity. One is the instantaneous, second is average, and the third is uniform. So for the instantaneous velocity, it is defined as the limit of the average velocity as the time interval becomes infinitesimally short or as the time interval approaches 0. And the equations, we're taking the small interval of time which approximately near to 0, so delta t approaching 0, and then we're going to take a limit of the difference between the displacement over time interval. And then these definitions will be using as the velocity, which is v is equal to ds by dt. So the second term which we're gonna using is the average velocity, which is defined as the change in displacement divided by time interval of that displacement. So which the equation is given as v average, which that is the symbol for average velocity. And since it says a change, so the symbol is delta. Delta s is a change in displacement. By means division over by time interval delta t. So the change means that the final displacement deduct with the initial displacement. So s2 minus s1 divided by the time 2 minus the time 1. So this is the average velocity. Then the last one is the uniform velocity, which is defined as the motion that doesn't change in speed nor direction. Or we can say is that the motion that travels equal displacement per equal time interval. So the equation is given as v is similar with the instantaneous velocity, v equal to ds by dt. Only that uniform velocity means that that velocity would be constant. So next part, we're going to learn about the linear motion with a constant acceleration. So in these simulations, we are seeing a car which is speeding, then suddenly seeing a traffic light goes to red. So the car brakes. So the velocity change from certain velocity becomes zero, and then going back to accelerations from zero velocity to a certain velocity. That means those two situations involving acceleration, constant acceleration. So the same as the velocity, acceleration has its own terms as well. So we're going to learn three terms of acceleration. One is the instantaneous, second is average, and the third is the uniform accelerations. For the first part of instantaneous accelerations, it is defined as the instantaneous acceleration is the limit of average acceleration as the time interval approaches zero. If you still remember that these definitions of instantaneous acceleration is almost similar with the instantaneous velocity, which shows an equations like A as the symbol for acceleration, dv by dt. And since the velocity, as we defined before, as the v equal to ds by dt, so we have twice differentiation. So d per dt times with the dv, ds per dt. So we have twice differentiations given as d squared s per dt squared. So it's easier if you just remember the A is dv per dt and the v is as well is as ds per dt. For the second terms, the average acceleration is defined as the change in velocity divided by time interval, which shows equation similar to the average velocity. So which the symbol as A average equal to the interval of v by delta t, which shows meaning that final velocity minus width, initial velocity over time interval. And the last term is a uniform acceleration, means that the motion of the object is getting faster or slower at the same rate, or the same change in velocity over a set of period of time, which shows equations of A, similar with the instantaneous acceleration, A dv per dt, but since this is a uniform acceleration, so the acceleration would be constant. So next part that we're going to learn is to know what's the physical meaning of three types of graph. One is the displacement time, st, velocity time, vt, and the acceleration time, at. So shows the graph of st, vt, or at as in the slide. This graph shows a straight line, meaning that at initial position, maybe an object is initially at a certain position, at rest, doesn't move. So v is 0, t is 0, s 0, a 0, meaning that this object doesn't move at all. So as it goes by, then this object will going for a certain movement. So we're going to learn what's the area under this graph and also the gradient under this graph. Just remember that we're not just having one graph, but we're going to have three a bit similar graph, st, vt, at, which shows a straight line graph. So for each part of the graph, we're going to have to learn the gradient and the area of the graph. For the graph st, the gradient of the graph represents the velocity. To ease you to know why does that gradient as a velocity, you can think about the unit of each of the quantity. For example, s, the unit is meter, t, time, the unit is second. So the gradient is change of y per change of x, meaning that delta y per delta x. So delta y represents by the displacement and delta x represents by the time. So thinking about the unit, the y and the x-axis shows unit of meter per second. So that's why it shows as the velocity. as represented by the gradient. You can think of this for the next part of the graph, which is VT, which give you the unit as a meters per second. So there are 2 per second, means meter per second squared, shows accelerations. And you can have a guess what's the gradient of the graph for the graph AT then. So think about the AT. What's the unit of accelerations A? Yes, correct. It's a meter per second squared. And then what's the unit for time? Correct, that is a second. So meter per second squared per second. So meaning that we're going to have 3 times per second. So no quantity is represented by the meter per second cube. So that's why under the gradient of the graph AT doesn't represent any quantity. Okay, so now think about the area under this graph, ST, and AT. Start with the graph displacement time. So shows the area. The area represented by the graph is the shape as a triangle, right angle triangle. To think about the quantity represents of area under the graph, you can think of the unit as well. So this is the shapes of a triangle. So think about the area, the unit of area of a triangle. So for ST, S is a meter, time T is a second. So multiply, because the area of the triangle is half times the base times the height. The base is in a unit second time, and the height is in a unit meter, which is the displacement. So the area under the graph is as a meter second. So what's the quantity represent of a meter second? Yes, correct. There is no quantity represents as a meter second. Okay, so there is no quantity of area under the graph of ST. Okay, so next part is the VT. The area under the VT graph is the displacement. Why so? Because the unit. Think about the unit of V, which is a meter per second. Okay, and then multiply, the meter per second is the height, and then multiply with the base, which is the second. So meter per second times second. So the second and the per second will be cancelling. So just leaving us with the unit of meter. So this area under the graph of velocity time is represented by the displacement. And then we can do the same for the area under the graph for graph acceleration times. Just multiply the height, which is meter per second squared, and the base, which is second. So leaving us with the meter per second. So that's why the area under the graph is represented by the velocity. So that's it, the contents of the first part of chapter 2. So I'm giving you 2 exercises to practice on the concepts that we've just learned before. So just take some time to read through the first exercise. So let me read it through for you. It says figure 1 shows displacement time graph of 2 cars, P and Q. Which of the following statements describe correctly the motion of the 2 cars at time t? So look at the graph. The graph given in the question is the displacement as a y-axis and the time as the x-axis. So this is as t graph. So shows 2 curves, one curve P, one curve Q, and then they both intersect at time t. So this first exercise asks us to correctly describe the motion at time t, meaning at this intersection. So read through these answer A, B, C, and D. I'm gonna give you some seconds. Maybe you need 30 seconds to answer this question. Well done for those answer A. The answer is A, which is the speed of Q is smaller than the speed of P. For those answer A, you may think about the concept we just learned, which is the gradient of the graph and as well as the area under the graph. Okay, so the answer is A because it says the speed is equal to the gradient of the graph and the gradient of Q is smaller than the gradient of P. Okay, let me go back to the previous page. Okay, let me go back it. So the gradient Q shows a smaller gradient compared to P at the intersection T. So this is more steep compared to the Q. The gradient Q is less steep compared to the P. I just say it another way around. So the gradient of the graph ST represents as the speed. So that's why the answer is A. Answer C and answer D both are wrong, okay? Because it says accelerations of P is equal to the accelerations of Q. Acceleration doesn't represent any of neither gradient nor the area of ST graph. So that's why C is wrong. And D, displacement P is greater than displacement of Q. Wrong, because again, displacement doesn't represent any gradient nor the area of the graph. Okay, so now we're gonna see the second exercise. So I'm gonna give you some time to read through the questions and I'm gonna go back to you. So these questions shows the velocity against time for the motions of an object. So the question asks you to think of which statements A, B, C or D is true regarding the motions of this object. So this object from T1, it has a velocity V1, and at T2, it has a velocity V2. So which statements A, B, C or D is true?